studied that in the process that there are different types of ores. So first of all, the process of extraction of metal is called metallurgy. Okay, the process of extraction of metal is called metallurgy that we have studied in the previous classes. Okay, and moreover, we have studied about the uh, there are some metals that exist in native and combined state that we have studied in the previous class. Okay, uh, along with it, we have studied that there are some metals that exist in the native state. There are some metals that exist in the combined state. Combined state means in the stable forms of carbonate, sulfide. Okay, then we have studied what is minerals and what is ores. Those minerals from which metal can be extracted out conveniently easily is called ores. Okay, next one is we have studied that there are the different methods that we're going to study in the in this process. And what are those methods? Tell me, what are those?
Roasting and calcination.
Yes, we are going to study that one also. Okay, what? Okay, so let's talk about this one. So we have studied that first of all we will select the ore from the minerals that which mineral is suitable for extracting out a particular kinds of ore. Okay, after that one we crush the ore. Okay, after crushing the ore we remove the impurities from it by using different methods like gravity separation. Okay, like hydraulic washing. Gravity separation and hydraulic washing is same. Froth flotation method. Okay, magnetic separation. So we remove the impurities from it, and then we bring we can say that now we have removed the impurities, okay, from the ores. Now if we have zinc sulfide plus impurities inside it, then it has been converted into zinc sulfide. Okay, if we have means if we have impure zinc sulfide, then we convert it into the pure zinc sulfide. Okay, understood?
Yes, sir.
If we have calcium carbonate plus impurities in it, so we remove the impurities, now it is pure. Okay, now what we are going to do here, we have four types of ores. One is halide ore, which is going to have halogens like NaCl, KCl, calcium chloride. Okay, these are the halogens, halide ores. Okay, and the next one we have carbonate ore, carbonate ore, which is going to have Ca. Okay, CO 3, which is going to have CO3 group at the end. Okay, Na2 CO3. Okay, Zn CO3. Okay, so we have carbonate ore, which is going to have CO3 in the end. Then we have sulfide ore. Sulfide ore is that ore which is going to have sulfur at the end. Okay, like Zn sulfide, like HGS, like we have Cu2 as copper pyrite. Okay, so there are different types of ore. These sulfide ores. So what we are and oxide ore is like which is going to have oxygen at the end, like Al2O3 dot 2H2O. This is bauxite ore. Okay, and then Fe2O3. This is oxide ore, oxygen at the end. Now we are just going to convert this carbonate ore and sulfide ore into their oxide form. Why we are doing this? Because it is easier to extract out metal from their oxide form rather than their means it is easy. If we have calcium carbonate, if we have zinc sulfide, and if we are extracting metal from this one, it is difficult. It is difficult. Okay, you understood what I'm saying here? So we are just converting this into this form, this into this form. So we are just converting. Okay, understood?
Yes, sir.
So what we are going to do here is we do the calcination. Okay, what happened in the calcination? Calcination is done for the oxide, so sorry, carbonate ores, and in carbonate ores, CaCO3 like we have, because it is already having oxygen, right? Plenty of oxygen. So when we heat it, it will gives you Cs calcium oxide plus carbon dioxide. No additional oxygen supply is being required here. So what we are going to do here is we just simply heating it, and we just heat it at 900 degrees Celsius. Okay, so that is converted into oxide form. Okay, understood? Understood?
Sir,
Yes.
sir, is it important to heat 900 degrees Celsius?
Yeah, different ores have different decomposition temperature. So this get decomposed at the temperature of 900 degrees Celsius. Okay. Below that
Oh,
temperature, if you start heating it at 100 degrees Celsius, it will not decompose. Okay. It will not gives you carbon dioxide. So what are the advantages? First advantages is that it gives you oxide form. What is the advantage of calcination? It will gives you oxide form, which is easily reducible. Means reducible means that it can be the oxygen can be removed easily. Okay. So this is called it is easily reducible. Means it can be easily reduced. Means it calcium oxide can be easily converted into calcium only. Okay. Understood?
yes, sir.
Yes, sir.
Okay. Now, if we have some volatile impurities, what do you mean by volatile impurities? Volatile impurities means that if we are having some impurities that is uh, volatile means that can be melted at low temperature. Okay. So if there is some this type of impurities is present, then this can be we can say that by this method these impurities can be liquefied easily, because if we have for example, if we have some impurities that can melt easily with low temperature. Okay. So when you start hitting it, if it has have it still have some impurities that can melt, like say for example at 500 degrees Celsius or 400 degrees Celsius, so they can be easily separated out, okay, from this one. So volatile impurities can be separated by this method or removed by this method. Okay. Okay. So,
Yes, sir.
so what is calcination? Calcination is the process of heating carbonate ore in the presence of in the absence of oxygen. Okay, in the absence of oxygen to give metal oxides and carbon dioxide. Okay. Okay. Understood?
Yes, sir.
And what is
Yes,
roasting?
sir.
What is roasting? Roasting is heating of sulfide ore, like we have ZNS, like we have Cu2s. Okay, if we start heating this one, but you need to give the temperature. You need to give external oxygen to this one, because you need to convert ZNO. And here is no ZNO, means there is no oxygen present here. Like in calcium carbonate, we have already oxygen, but in zinc sulfide, there is no oxygen. So we need to give oxygen, external oxygen from it to it, and then we heat it at high temperature, and then it will gives you ZNO plus sulfur dioxide. We can balance it later, but this is the result. Okay, that when you heat it in the presence of oxygen, it will gives you oxide form. Okay, understood? And similarly, we heat it copper oxide and we heat it continuously, and it will gives you Cu2O plus SO2 sulfur.
So if we heat ZnO, then it will give Zn plus O2, right?
No, if we
No.
heat only ZNO, it will not give you Zn plus O2. We need some reducing agent. We're going to discuss this one later. For like for example, if you have HGS, Hg2s, okay, and if you heat it in the presence of oxygen, it will gives you HgO plus SO2. And when you heat this one, AgO, Ag2O further, okay, then it will gives you Ag plus SO2. So here it can gives you, but since zinc is more reactive, so we need a reducing agent. So if we alone heat it in the heat it like this way, it will not gives you. We will discuss this one. We are not going to do that one. So what is roasting? Roasting is simple. When we start heating an element, okay, and a sulfide ore in the presence of oxygen to gives metal oxide. Okay. And what is the advantages? Sulfide ore is converted into oxide form, which is easily reducible. And the next one is, tell me, next one is volatile impurities can easily be removed. Okay. Understood?
Yes, sir.
So please
Yes, sir.
note it down. Note it down, roasting, calcination, and their advantages. Done. Done this one, Karishma. The lamp.
Yes, sir.
No, sir. 1 minute.
Note it down fast.
Sir,
Yes.
sir, in roasting, will there be a limited oxygen or
No.
more?
Sufficient supply of oxygen should be there.
Okay, sir.
Done.
Sir, can you please scroll?
Okay.
Done, sir.
Done, everybody. Done, everybody in the
Yes,
class.
sir. Yes, sir.
Okay.
Yes.
Is there anyone still writing? Should I move further?
Yes.
Yes, sir.
Okay. Okay. Now moving to the next part is now we are going to how can we remove the now we have converted the carbonate ore into the oxide form. Okay. Sulfide ore also they are into their oxide form, and oxide forms are already oxides or are already in oxide. For example, we have zinc carbonate or zinc sulfide or calcium carbonate. We have them converted into ZNO. Okay. We have converted this into ZNO. This one also CaO. Okay. If we have Hg2s, we convert it into HgO. HgO. So if we have different elements, okay, and we have in their sulfide or carbonate ores, we have converted into their oxide form. Now, how can we convert this oxide into their metals? Means how can we get this ZNO be converted into Zn? This ZNO can be converted into Zn. Then calcium oxide need to be converted into calcium. Okay, how can we convert it? Okay, so this is called reduction. So how we do the reduction? So let's discuss about the reduction. Okay, reduction means removal of oxygen. Okay, understood?
Oxygen. Yes, sir.
Oxygen. So we have low reactive metals that are low hydrogens. So for low reactive metals, we are just asking for low reactive metals. Okay. If we have low reactive metals, low hydrogens. Okay. So that is like copper. Copper exists in the form of Cu2s. Exists in the form of HGS. Okay. Silver exists in the form of HGS, Hg2s. Okay. So how can these be converted? So they can be converted. Okay. Low reactive metals, and here we have below hydrogen. Okay. Below hydrogen in the reactivity series. So if we have these metals, these are low reactive metals. These are low reactive metal ore. Okay. And they can be separated out there. They can be reduced by simple roasting. If you roast them, then they can be simply eliminated out. Okay. For example, if you have Cu, for example, if you have Ag2S, you heat it in the presence of oxygen, roasting. Okay. You are doing roasting here. So it will first convert it into AgO, Ag2O, and then sulfur dioxide. And when you continuously heat it, on continuously heating, okay, continuous heating, okay, or we can say that if you continuously heat it, or write it again, Ag2O, when you continuously heat it, it will gives you Ag plus O2. Understood?
Yes, sir.
So here it will get converted into on continuously heating. Similar is for the Hg also, HGS also. Similar is for HGS also. Hg2S, sorry, HGS, when you heat it in the presence of oxygen, it will gives you Hg
O plus
plus
SO2.
SO2. Now, when you continuously heat it, HGO will get converted into Hg.
Sir, here it should be HGO, right? You wrote HG only.
HGO, yes. Okay, we are heating it. Okay. So it get converted. Okay. But there is a special case of a special case. There is a special case of copper sulfide. Okay, this is a special case. A special case of Cu2S. If you heat it Cu2S in the presence of oxygen, it will first get converted into Cu2O plus SO2. But if you heat it alone, like you are heating here and here, it will not gives you Cu. It will not gives you Cu. Okay, why? Like here it is giving you Cu if you heat it oxygen. Here it needs some reducing agent. It needs some reducing agent. Okay, it is reactive than these two, and it needs some reducing agent. But if we heat it Cu2O with this crushed ore, Cu2S, then it will gives you Cu plus SO2. Okay, so we have to write here that in case of copper, crushed ore itself behave as reducing agent. Crushed ore itself behave as reducing agent. Okay, please note it down.
Sir,
Yes.
so why can't we heat alone Cu2O?
If you heat it, it will not gives you. Means if you heat it alone, if you go to the market and for somewhere, if you bring Cu2S, sorry, Cu2O, and you heat it, it will not gives you Cu plus O2 because it is more reactive. Okay, it is more reactive. It needs some reducing agent. Like for example, if you have ZNS, okay, and you heat it in the presence of oxygen, it will first give you ZNO
ZNO plus SO2.
plus SO2. And if you further heat it ZNO, it is more reactive. So if you heat it, it will not gives you Zn plus O2. No, it will not gives you. You need some reducing agent. And here for this one, we use carbon. It will gives you Zn plus CO2. Zn plus CO2. So here carbon is used. Carbon is used as reducing agent. Okay, you understood? But
Yes.
here carbon is, you have to bring it away from, means if you have to, you need to go to the market and you need to bring the carbon. But here in case of Cu2S, if you heat it in the presence of oxygen, it will give you Cu2O plus SO2. And further, if you heat Cu2O, then if there is some particles, okay, means means some of the particle get converted into this one, and this particle start reacting with this one, okay, which is still in the container, some portion which is still in the container, okay. So it is not instantly first forming this one, as some of the particle get converted into this one, then some of the particle will start converting into reacting with this one. Okay, so here you need not to go to the market. Here the crushed ore itself behave as a reducing agent. Okay, Cu2s. When you heat it together, the mixture of this one, it will give you Cu plus SO2. Here the crushed ore it's itself behaving as a reducing agent. You understood? Understood everybody in the class?
Yes, sir.
Yes, sir.
Okay. So please note it down. Done?
No, sir.
Note it.
Done, sir.
Is there anyone who's still writing? Is there anyone? Is there anyone? No? Okay, so here this is written that, okay, that this is Cu2s in case of copper. It will give you Cu2O plus sulfur dioxide. And then this Cu2O react with Cu2s, it will give you copper plus sulfur dioxide. Here crushed ore itself behave as a reducing agent. Okay. Have you written this one? That the crushed ore itself behave as a reducing agent?
Yes, sir.
But now we have mid-reactive metals. Okay. What are mid-reactive metals? Mid-reactive metals.
Those are in mid in
Yeah.
reactivity series.
Yeah. After the aluminium, okay.
Yes,
Like
sir.
we have
Zinc, FePbN.
zinc, Fe, Pb, okay,
U.
and Sn, okay. So these are the metals that are in the mid of the reactivity series, and this can be reduced with the help of carbon. Okay, so this can be reduction with the help of carbon reduction with the help of carbon. Okay, so if we have zinc oxide, so we need carbon. Okay, we heat it with the carbon, it will give you Zn plus CO2. Okay, Zn plus CO2. Similarly, if we have PbO, Okay, it is already in the form of PBS, but we have converted by roasting already in the form of PBO. Okay, now PBO, when react with carbon, it will gives you Pb plus CO2. Okay, understood? Similarly, Fe2O3, when react with carbon, it will gives you Fe2O3 plus CO2. Sorry, Fe plus CO2. What it will gives you? Fe plus CO2. Okay, understood? Understood?
Yes, sir.
So this is called reduction with carbon, with the help of carbon, and reduction of with the help of carbon is called smelting. Reduction with the help of carbon, help of carbon is called smelting. Okay, so mid-reactive metals are being reduced with the help of the reactive metals oxides are reduced with the help of carbon. Okay, why we are choosing carbon? Because carbon is economical and easy and convenient. Okay, understood?
Yes, sir.
Understood? Okay, like we have this one. Note it down. Reduction with carbon is called smelting. Mid reactive metals can't be reduced by simple heating. Okay, heating. They require suitable reagent for the reduction, and the reduction by using carbon is called smelting. Note it down. When you're done, please let me know. Okay.
Yes, sir. Done, sir.
Done. Is there anyone who's still writing?
Yes, sir, just 1 minute.
Okay.
Done, sir.
Done. Okay. So let's move further. So these are Fe2O3 that we have studied. If we have zinc oxide, then it can be converted into zinc and carbon dioxide. Now, the metals which are above the carbon, okay, we can say mid-reactive metals. Above the metals that are above the mid-reactive metals. For example, if we are having aluminium, sorry, manganese and chromium, okay, manganese and chromium, okay, and chromium. So if we are having, like for example, if you are having manganese oxide, MnO2, and and like we have chromium oxide, Cr2O3. Okay, chromium oxide. So they can be reduced with the help of aluminium. So manganese and chromium oxide can be reduced with the help of aluminium. Okay, and this is called alminothermy. Okay, what we called it? Almino reduction with aluminium is called
Aluminium.
alminothermy. Okay, so if we have this one, and if we react this manganese oxide with aluminium, then it will gives you Mn. It will gives you Al2O3 plus Mn. Okay, in the liquid state. Similarly, if we have this chromium oxide, it will gives you Cr2O3, sorry, Al2O3 plus chromium in the liquid state. Okay.
Sir,
Yes. Tell me.
Mn and Cr are high reactive or middle or low?
No, it is not, neither so highly reactive nor it is mid reactive. It comes intermediate. Okay. So if we
Okay.
have intermediate, no, neither it is mid reactive nor it is above the mid reactive. We will discuss this one. Let me write this whole table here. So if we have like we have sodium, potassium, sodium. Okay, potassium, sodium, calcium, magnesium. Okay, these are highly reactive. Highly reactive. Okay, and if we have like we have aluminium. Okay, then we have manganese and chromium here. Okay, then after the manganese and chromium, we have zinc, but I'm just placing carbon also here because these metals that are below here can be reduced with carbon. These can be reduced with aluminium. Okay. Okay. So this is iron, sorry, zinc, iron, lead, tin. Okay. So these can be reduced with carbon. Okay. So this is smelting. This is alminothermy. Alminothermy. And below this one, below hydrogen, like we have copper, silver. Uh,
AU.
yeah, they can be reduced with the help of simple roasting. Simple roasting. You understood? By simple
Yes.
roasting, you can do this one. Okay. So this is the way how we do this one. Okay. Now, if we have MnO2 react with aluminium, it will gives you Al2O3 in the liquid state. If we have chromium oxide reacting with aluminium, it will gives you Al2O3 in the and chromium in the liquid state. You understood? Are you getting my point?
Yes.
Now you need to understood one thing here is that that the metal obtained here is in the liquid state. I'm writing here liquid state. Why it is in the liquid state? Because the heat liberated out during this reaction is so large and so high that the metal obtained is in the liquid state. Okay. And for this we use Fe2O3 also. When it also react with the aluminium, it will gives you Fe. It will gives you Al2O3 plus iron in the liquid state. Okay. It will gives you.
So it is also known as molten state something.
Yeah, it will. The iron obtained here is in the liquid state, and we will say that this type of reaction is called thermite reaction.
Since this reaction is also used for joining
Joining
Yes,
the
sir.
scaffolding
derivative. Yeah,
and
Elevatrix is.
machine parts
yeah.
and machine parts.
Yeah. Let me show you this reaction. How this reaction take place. Today I'm not well. That's why I'm just co- having cough. Okay, so it might be. So let me show you that how this reaction is thermic and uh, how it is used for joining the railway track, because we can reduce Fe2O3 with the help of carbon also. But here that in that case, when we are reducing with carbon, the metal is not obtained in the liquid state. Okay. And that reaction was not so spontaneous, not so fast. But here, if we react with the aluminium, uh, uh, and aluminum powder react with the Fe2O3, then the iron obtained is in the liquid state. So let me show you. So in that case, we can simply say that the metal obtained is in liquid state because this reaction is so exothermic. Okay. So here you need to note it down. Note it down. This one. Note it down. Aluminothermy is reduction with aluminium. Write this reaction. Okay, write this one also. And this is known as thermite reaction used for joining railway tracks and broken machineries. Reduction with aluminium is exothermic process. The heat liberated out during this process, this reaction is so large that the metal obtained is in the liquid state. Note it down. I'm writing a portion from here. So large that the metal obtained is in the water. Done?
No, sir.
Note it down.
Done, sir.
Yes, sir. Done.
Everyone?
Yes,
Done?
sir. Yes, sir.
Okay. Next is electrolytic reduction of sodium chloride. Okay. So if we are for highly reactive metals, what we do? Electrolytic reductions. Okay, so where was that chart? So if we have mid-reactive metals, they can be reduced with the help of carbon. The aluminium, the metals which react with aluminium, okay, like
Metal.
manganese oxide, okay. But if you are talking about the metals that are above, like we have sodium chloride, potassium chloride, okay, magnesium oxide. So these are highly reactive metals, okay, Al2O3. So Al2O3. So these are highly reactive, and for this one we use electrolytic reduction. Electrolytic reduction method. Okay. What we does, for example, if I'm just taking the example of sodium chloride, okay. So if we take the example of sodium chloride, if we take the example of sodium chloride, so what is done here is we take two inert rods. Inert rods means they do not participate in the reaction. Okay. This is positively terminals. And this is negatively charged. Okay. And we have molten NaCl inside it. Don't use aqueous, only molten. Okay. Molten NaCl. So what we are using here? We have molten NaCl. Molten NaCl, sodium chloride. So when we heat it and it get melted, then what is going to happen? What is going to happen? You will notice that this is NaCl. Okay. It is in the liquid state. And when you heat it in the liquid state, then this Na
Plus Cl.
and Cl2 gas will be formed. Okay. Na solid and Cl2 gas will be formed. Na, since it is positively charged, it will form at cathode. At cathode, and the chloride ion, the Cl2 is Cl minus ion. So it will form that anode, anode on positively charged anode. Let me explain you. If this is Na positive ion, Na positive ion, okay, another one is Cl minus ion, that this is Cl minus ion, Cl minus ion, okay. So what is going to happen? This Na will move towards the positively charged rod, sorry, negatively charged rod. So this will move here. And this Cl minus ions will move toward this. Okay. This Cl minus ion will move towards this positively charged rod. Okay. So what would happen at anode? At anode, the 2 Cl minus ion will goes and will donate its electron. Will donate its electron and will form Cl2 plus 2 electrons will be loosed. Okay, because 1 Cl minus ion means it is going to have 8 electrons. 7 is already present, 8 is borrowed, that's why it is minus charge. Another one is also 1, 2, 3, 4, 5, 6, 7. These are 2 Cl minus ion. So in order to make chlorine gas, they have to release their 1 electron. When they lose 1 electron, their charge will disappear. And now they can make sharing bond. Okay, each of them is going to carry 8 electrons. Okay, now this forms Cl2. So for Cl minus ion to become Cl2, they need to lose their electrons. 2 Cl minus ions will lose 1 electron and will form Cl2. And at cathode, what is going to happen? The 2 Na positive ions will go and will receive these 2 electrons. Okay, will receive these 2 electrons and will form Na solids. 2 Na solids means Na when gets Na positive, when gets 1 electron, it become Na solid. Okay, Na atoms. Okay, understood? So
Sir?
overall reaction is this one. Yes.
Sir, could you please explain it why Cl negative is going positive, like why it's going anode side?
Because negatively charged is always attracted towards a positively charged species, towards a positively charged rod. So this is positively charged and these are negatively charged. So opposite charge attract each other. Okay,
Yes, sir.
that's why negatively charged. So when we pass electricity to it, and it will give you overall reaction is this. Okay, are you understood?
Yes, sir.
So this ABCD you need to remember that at anode chlorine gas will be formed, because the question comes in examination like this way. And a metal chloride X, a metal chloride X when react with when heated, okay, then it gives a gas B which is produced at anode, okay, and which is also used for preparing bleaching powder. So chlorine gas is used at bleaching powder. Okay, so it may be asked that find X, Y, Z and X, Y, Z. So this can be question. This type of question can be asked in examination. So you need to remember properly that which is used for this one. Okay, so please note it down. Note it down. This one. At anode, oxidation takes place always. Okay, and at cathode, reduction takes place always. So note it down. While you're done, please let me know, okay?
Okay, sir.
Done?
Yes, sir.
Everyone done?
Yes, sir. Sir,
Yes.
sir, could you please explain it again? That CL part.
Okay. The Cl part is that means that is Cl.
No, it
Okay.
is the electrons, like the atoms 7 and 8.
Yeah,
The
yeah,
electrons.
that's the same. The same I'm going to repeat. If Cl is going to have it has 7 electrons in its outermost shell. Why? Because it has 287 electronic configuration. Atomic number is 17. Okay, that electron configuration is 287. It has 7 electrons. If it suppose acquire 1 electron from somewhere, so it complete its octet and become 288, but it will acquire 1 negative charge over it. Okay, it will acquire 1 negative charge over it. Why it is acquiring 1 negative charge?
Complete
Bec-
the shell.
yes, in order to complete the shell. So it is now having 8 electrons because it has borrowed 1 electrons. But in order to form Cl2, so Cl2 is formed between atoms, 2 chlorine atoms. Now it is chlorine ions. To become again chlorine atom, which is this one, okay, it has to lose one of its electron. So if two Cl minus ions come together, okay, and they want to make bond to form Cl2, then they have to lose 1 electron. This will lose 1 electron, this will lose 1 electron, and then now they will make a sharing bond, which is called covalent bond. It is formed here, and okay, and this will be formed. Okay, understood? Understood? So here the
Yes,
two atoms will share 1, 2, 3, 4, 5, 6, 7, 8. Each of them is going to have 8 electrons. This is called sharing bond. The Cl atom will combine together now. This is Cl2 gas formation. So Cl minus ion cannot make bonds. Cl atoms can make bonds, covalent bond. Okay.
Yes, sir.
So there is one last topic is remaining. That is electrolytic refining. Okay. And there are so many questions over that. But should I explain you this one? Okay, let's try. If I'm talking about the electrolytic refining means now we have just by different methods we have obtained metals from their oxide, from their halide forms, okay, from their sulfide forms. Now metals has been obtained. Okay, like if we are having zinc oxide, now we have converted it into zinc. If we are having Al2O3, now we have converted it into Al. If we have NaCl, then we have obtained Na by electrolytic reduction. Now still the metal that we are obtaining here, is it 100% pure? Pure does not mean here that it is having impurities like soil sand. No, purity means that is it having all the items of same kinds? Is it the mixtures of some, means for example, if we are having a copper metals, if I'm having a copper metal loads, so is it still having a copper? Okay, is it still having a copper, all copper items, or is it having a mixtures of aluminium, like gold, like platinum, some other elements? So
Sure, it will have, right?
yeah, it will have, right? So this will be considered as impure metals. Okay, impure. So there is a method that we use for refining the metals, and we called it electrolytic refining. Electrolytic refining method. Electrolytic refining method. Okay, what happened in that one? We have two rods. One is thin rod, and another one is thick rod. And one is connected with the positive terminals, another one is connected with negative terminals. Keep in mind that the rod which is connected with the cathode or negatively charged rod, it is called impure rod, impure metal rod, and another one is called, sorry, it is pure. I'm writing here. It is pure metal rod, and it is impure metal rod. Impure metal rod. Okay, understood?
Yes, sir.
So what is going to happen here is, if we have this pure and impure metal rod, so we just have just a salt inside it, the same metal salt, same metal salt is taken. Okay, for example, if we are just purifying copper rod, okay, so this will be considered as, this rod is considered as pure copper metal rod. Okay, pure copper metal rod, which we will bring it, and this is which we need to purify. Okay, this is impure copper metal rod, impure copper metal rod. Okay, understood? Impure copper metal rod. And here the salt of same metal, for example, if we are just purifying, so it must have Cu2 positive, means we have copper sulfate salt inside it. Okay, Cu2 positive and SO4 minus 2, Cu2 positive and SO4 minus 2, Cu2 positive and SO4 minus 2. It's the same salt. Okay, copper sulfate. So if we are purifying copper, then we will have copper sulfate here. If we are purifying silver, then we will have silver nitrate here, AgNO3. Okay, the same metal that you are purifying, same metal pure rod will be taken here, and same metal impure rod will be taken here. Understood? Understood?
Yes, sir.
So I think we will continue this topic in the next class. Okay, because other batch students are joining. So I'll continue this one in the next class. This is the last topic that we going to discuss, and this is an important. Then we'll start carbon compound chapter, because since this is an important topic, so I'm not going to do it in the rush manner. Okay, so we'll discuss this one. This is very important. So we'll discuss this one in the next class. Okay, that's all for today. We'll meet you in the next class. Okay.
Okay, sir. Thank you, sir.
Okay, so thank you.
Okay, take care, everybody. You can leave. Hello, Abdul. Are you there?
Yes, sir.
Are you in which standard you are? 10th standard, na?
Ninth.
Ninth. Oh. So you recently joined it. Is it your first class?
No, no, sir. I'm waiting for my class. They said it will.
So is it your first class with me?
No, sir.
So wait a minute. Wait a minute. Let me confirm whether you are having the same class here or some other teacher's class. Okay, wait a minute.
I'm having here class, but another teacher. Maths.
With another teacher. Okay. So uh how many class have you completed here?
Of maths or what, sir? I
Yeah,
did not
of
understand.
maths, of maths, of maths.
Maybe 10, 20, 12, like this.
Okay, wait a minute. Wait a minute.
Hello, sir.